We are here, and here is a distant galaxy. We know that the universe is expanding and also accelerating, and the farther the galaxy is from us, the faster it is moving away due to the expansion of the universe. And if it is far enough, it will be receding from us, faster than the speed of light. For now, let's ignore the question of how this is even possible and just accept it. So if the galaxy is receding faster than the speed of light, how can we see it? How can we receive a signal from it? Intuitively, one might say no, but there is a catch.
As strange as it may seem, the answer is yes. Under certain conditions, we would actually be able to see a galaxy that is not only currently receding from us faster than light, but was also doing so at the moment it emitted the photon.
What? But that's not the only counterintuitive thing in cosmology, and not the only one we will be talking about today.
Today we'll talk about the observable universe, its quote-unquote edge, its horizons, and many other interesting things.
My name is Andrei, and this is Cosmos Elementary. It shouldn't be surprising that when we say observable universe, we mean the part of the universe that we can see. And the boundary of this observable universe is the first horizon we will talk about today, the so-called particle horizon.
The entire universe is larger, possibly even infinite, but we only see a finite limited region of the universe. This is because, according to modern understanding, the universe in its current form has not always existed.
So it has a certain age, and also the speed of light is finite.
So since the moment of the beginning of the universe's expansion, or the Big Bang, which occurred approximately 13.8 billion years ago, light could only travel for 13.8 billion years. A little less actually. But fundamentally, the particle horizon is at the distance from which light has had enough time to travel to us since the birth of the universe. It can be worded slightly differently. The particle horizon is the farthest distance from us from which we could potentially receive information from the past. From the past.
I think it will be no surprise for many of you that we observe the universe and basically everything around us in the past, since the light emitted by or reflected off of even the closest objects takes time to reach us.
So that's basically common knowledge, but still, when it comes to the scales of the observable universe, this aspect becomes particularly important. You may have seen this image. Oh, by the way, although it doesn't have much practical significance, each of us has our own slightly different observable universe. After all, it represents a sphere with the observer at the center.
And you, who are watching this video right now, may be hundreds or even thousands of miles away from me. Your particle horizon, in a certain direction, is slightly farther than mine.
But let's return to this image. It looks beautiful and it is quite informative. Obviously it is not to scale, but that's not the point. And it's also important that even if we ignore the scales, right now, at this very moment, we observe the universe like this. But again, it doesn't look like this in more distant regions at this exact moment in time, because what is shown here is the past of the universe, the past that we see from the present moment at the center to the earliest epochs at the edges. But in the present, everything inside the circle more likely looks like this. Right now, we're observing the cosmic microwave background at the edge, but that part of the universe doesn't differ much from ours on a larger scale. And conversely, if by chance at that point in space where we currently observing the cosmic microwave background, an intelligent civilization appeared and they directed microwave telescopes towards us, they would be observing the cosmic microwave background in our region of space.
Well, since I mentioned the cosmic microwave background radiation, I talked about it in more detail in my video about the axis of evil. But I'd like to add something, moreover, it relates to our topic today.
I mentioned that the cosmic microwave background radiation is the earliest stage of the universe that we can see, but here we need to clarify something. It's the earliest light, or more precisely the electromagnetic radiation that we can see. Because up until 380,000 years after the Big Bang, the universe was opaque to radiation, and the cosmic microwave background consists of the earliest photons we can detect.
But there's also something that hypothetically could give us a glimpse, in a sense, of what is beyond the CMB. In modern cosmology, there are predictions that there could also be another background radiation, the neutrino background.
Until about 380,000 years after the Big Bang, when the universe was in a state of dense hot plasma, photons couldn't freely propagate, much like photons deep inside stars. On the other hand, elementary particles like neutrinos weakly interact with matter, and they could propagate more freely even before the epoch of recombination. Similar to how we are surrounded by cosmic microwave background radiation, we could be surrounded by relic neutrinos, and they could provide us with information about an even earlier universe, up until 1 second after the Big Bang.
But the problem is that, unlike the cosmic microwave background radiation that we observe directly, the neutrino background has not been detected yet directly.
They have very low energy, they interact weakly with matter, and they are very difficult to detect, but research in this area is ongoing.
Also, hypothetically, it is possible to detect primordial gravitational waves, disturbances in the fabric of space-time, from the early epochs of the universe predating the appearance of the CMB.
In 2014, there was even an announcement of the potential detection of primordial gravitational waves in the polarization of the cosmic microwave background radiation, which was based on the data from the BICEP 2 telescope. However, later analysis using the Planck Observatory showed that the entire signal could be attributed to dust in the Milky Way. So in general, hypothetically, a signal even not in the form of light could be obtained from an even earlier epoch, but this has not been yet done.
Also, many times I've heard this question: why do we continue to see the CMB? Why doesn't it disappear?
I think the intuition here goes something like this. Take the sun, for example. We see its radiation as long as it exists and shines. If it disappears, we'll stop seeing its radiation. Since we continue to see the cosmic microwave background radiation, what is then shining at the edge of the observable universe?
But such an analogy with the sun is not correct. In short, as the universe, probably infinite universe, continues to expand, relic photons from new and increasingly distant regions continue to reach us.
Before recombination, when the universe was still in a state of hot plasma, let's say here was a point in space where Earth is located now. And here, surrounding it, is a region from which we are now receiving photons of the cosmic microwave background radiation. The region is called the surface of last scattering. But photons were emitted not only from this specific region, which we are observing right now as the surface of last scattering. They were everywhere. Photons from nearby regions reached our point almost immediately, and the farther they were emitted, the later they arrived. Let's say 3 billion years ago, relic photons reached us from here, later from here, and in the future they will continue to arrive from here, and so on.
However, this doesn't mean that we will continue to see it forever.
Due to redshift, the background radiation has shifted from the visible portion of the spectrum to the microwave range. But the expansion of the universe still goes on, causing waves to stretch even further. Eventually, due to redshift, it will become increasingly difficult to detect these photons.
By the way, the fact that we have observed and continue to observe the CMB indicates that the Big Bang happened everywhere and it had no center.
Which sometimes confuses people when they see images like this one. But they mostly just illustrate the chronology of events, and the word bang itself can also be misleading. And yet the Big Bang has nothing to do with the conventional explosion with the center. In the universe, there isn't a specific point from which the expansion began, just as there is no center to the surface of an expanding sphere. Now, let's return to the particle horizon, the boundary of the observable universe. How far is it?
And again, intuitively one might think that since the light had 13.8 billion years to reach us, that should be the radius of the observable universe, 13.8 billion light years. But we don't live in a static universe. It expands. If there are two galaxies separated by a billion light years and one emits a photon, In a static universe, a photon will reach another galaxy in 1 billion years, covering 1 billion light years.
In an expanding universe, with each passing second, a photon needs to traverse an increasingly greater distance. A popular analogy here is where the photon is represented by an ant crawling from point A to point B along a stretching rubber band which represents expanding spacetime.
As a result, the radius of the observable universe is much larger than 13.8 billion light-years.
Taking into account modern measurements of the expansion of the universe and the history of this expansion, the distance to the particle horizon is currently estimated to be approximately 46.5 billion light-years. So the diameter of this sphere in its present form is about 93 billion light-years. Also, here we can see that the region from which we currently observe the cosmic microwave background radiation, the surface of last scattering, is not the outermost layer. After all, in the first 380,000 years, space-time was already expanding, so the surface is actually slightly closer to the particle horizon itself.
What lies beyond this sphere? We don't know, and it's hard to even think of the way to check it directly. But most likely nothing special. More or less the same as we observe here in our region of the universe. As for how large the universe beyond the observable part, we also don't know for sure.
There have been estimates suggesting that it is at least 250 times bigger than our region of the universe. In general, this is related to the geometry of the universe. Under the assumption of the flat geometry of the universe, meaning it is not closed in on itself like a sphere, it could be infinite. Most scientists today lean towards this based on modern data. Therefore, our observable universe, despite its vast size, may only be a small part of the entire universe.
So, according to modern estimates, the age of the universe is 13.8 billion years and the radius of the observable universe is more than 46 billion light years. So clearly something beyond the speed of light is involved. But no, not motion, that's still impossible. But the expansion?
If we only consider the expansion of the universe, the region of space that is currently at the boundary of the observable universe is receding from us at a speed of more than 3 times the speed of light.
But according to the special theory of relativity, no object can move at the speed of light in the vacuum. But there is no violation of the theory here.
In this case, no objects are actually moving through space at superluminal speeds. However, 2 galaxies can be moving away from each other faster than the speed of light simply because space itself is expanding that fast. Let's return to this illustration of the expanding universe. Galaxies in their coordinates appear to stay in place, but nevertheless the distance between them increases. Granted, we are not considering the motions of galaxies within groups of galaxies here, but at scales where expansion becomes noticeable, we can ignore this for the sake of demonstration.
Here we have approached something that is sometimes called the Hubble Horizon, but it is not the horizon in the usual sense. It is also called the Hubble sphere or the Hubble radius.
This is an imaginary boundary in space beyond which objects are currently receding from us faster than the speed of light due to expansion.
The Hubble radius is calculated simply by dividing the speed of light by the Hubble constant. The Hubble constant is a parameter that describes the rate of the expansion of the universe.
As you may know, different methods today provide slightly different values for the constant, but if we take the average value, dividing the speed of light by the Hubble parameter gives us precisely 13.8 billion light years. So considering that the radius of the observable universe at the moment is 46.5 billion light years, everything beyond 13.8 billion light years is receding from us faster than the speed of light. However, somehow we can see the objects that lie beyond the Hubble sphere.
So what's the deal?
Our universe isn't just expanding, but it's expanding at an accelerated rate. Without delving into the details of how the Hubble constant changes, which over time is actually not constant, and some other nuances, the simple answer is as follows. The universe is expanding and the Hubble sphere is expanding too. Even if a photon was emitted in a region of superluminal recession beyond the Hubble sphere, in an accelerating expansion scenario, the Hubble sphere can effectively catch up with this photon. Then it enters the region of subluminal recession and starts moving towards us until we finally detect it. Everything we observe from the early epochs of the first 5 billion years of our universe has always been and is currently receding from us faster than the speed of light.
But let's look at it a little differently. I found a good explanation based on the modern data that uses a space-time diagram.
On the vertical axis here we have time, and on the horizontal axis we have the distance that existed between 2 points at a particular moment in time. There are actually various measures of distances because the universe is expanding.
If the universe were static and we detected a photon from a galaxy that is 1 billion light years away from us, the distance would indeed be 1 billion light years and there would be no issues.
In an expanding universe, at the moment when photon was emitted, there was one distance between us and the galaxy. And later, when it reached us, there is a different distance. That's precisely why throughout the video I said now and at the present moment when discussing distances. Scientists simply use different distance measures to account for this.
Now let's not delve into details here. It is also common to talk not only about the distance but also about the time it takes light from an object to reach us.
In this diagram, we can visually observe how the distances differ at the moment of emission compared to the current distance of a galaxy from us. Our galaxy is currently located here, and now we have detected a photon from this galaxy. This photon was emitted 11.3 billion years ago, or 2.5 billion years after the Big Bang. When it was emitted, our galaxy was temporally located right here. At that moment, there was a distance of approximately 5.5 billion light-years between our galaxy and the second galaxy. If the universe were not expanding, the emitted photon would have reached us along this trajectory after 5.5 billion years.
But it's expanding.
Therefore, the actual trajectory of the photon in the diagram looks like this. It reached us not after 5.5 billion years, but after 13.3 billion years. And it had to cover a much greater distance. Furthermore, we see that the galaxy itself continued to move away from us, and at the present moment it is located here. The actual distance from it to our galaxy at this moment is nearly 20 billion light years.
Well, what about the superluminal recession then?
Note that in this section, the photon was moving away from us due to the accelerated expansion rather than approaching us.
It is also important not to forget that the expansion of the universe is not linear, meaning it was not expanding always at the same rate.
In the early stages, the universe expanded very rapidly, then the expansion slowed down, and approximately 6 billion years ago, it began to accelerate again more strongly. At some point, the Hubble sphere effectively caught up with the photon, causing it to enter the region of subluminal recession. Consequently, it started moving towards us until we detected it. Here we can clearly see that the galaxy is currently beyond the Hubble sphere, meaning it is receding from us faster than the speed of light. However, the crucial point is that it was also beyond the Hubble sphere at the time of emission. And yet, due to the expansion of the universe, we were able to observe this galaxy. And the photons that we see today moved along curves resembling a water drop in shape, and they are called light cones.
But there is another question.
Can we see the light emitted by this galaxy now? Here the answer is no, because it is beyond another horizon, the event horizon.
So the last horizon we will discuss today is the event horizon.
And no, I'm not talking about the event horizon of black holes. They could come up with a separate name though, but what can you do?
The horizon acts as a barrier for events in the future that we can see.
Before this, we were discussing objects that we could see even if they are receding from us faster than light. But we were observing their past.
But if an object beyond the event horizon emits a photon, we will never see it. That's according to modern data. Well, unless something suddenly changes in the universe.
Currently, the cosmological event horizon is located approximately 16 billion light-years away, slightly beyond the Hubble sphere. Well, about how the universe will appear in the distant future for an observer from our vantage point, We'll probably talk about that separately. Oh, and it's worth reiterating that everything I've discussed today is based on modern data and our current understanding of the evolution of the universe, its expansion history, composition, and geometry.
And another thing. Imagine we have a spaceship that is capable of traveling at 99.9% of the speed of light.
And let's say right now there are two galaxies that we can see. One is inside the event horizon, the other is beyond it. And again, we can see both galaxies. If we were to board the starship, after an unimaginably long period we could eventually reach the galaxy inside the event horizon. However, we will never be able to reach the second galaxy that is beyond the event horizon. Never.